Hello everyone! In today's video, we are going over inferential statistics. This is part 2 in my Basic Statistics for Data Science series. Part 1 was over descriptive statistics, so if you missed that one, you can watch it over here. In this video, we will cover what inferential statistics is, sampling techniques, hypothesis testing, and finally we'll end with some examples of statistical tests using Python. So let's get right into it. First, let's define inferential statistics. Inferential statistics is an analytical tool used to make generalizations about the larger population by analyzing a smaller representative sample. We do this by forming a hypothesis, taking a representative sample, and using the results to infer probabilities or patterns about the larger population. For example, let's say you're working as a data analyst at a restaurant and the owner wants to know whether or not being part of a loyalty program has an impact on spending. Let's say you haven't rolled out the loyalty program to all the customers, you've only rolled it out to a sample of customers. You could use inferential statistics to see if that sample saw a change in spending after being part of the loyalty program, and what the probability is that that change that you see in the sample can be applied to the overall customer base. Next, let's go over some sampling techniques. Now, there are quite a few different sampling techniques that can help you get a representative sample of the population, but today I just wanted to cover 4 of them. The first is simple random sampling. This is where each member of the population has an equal chance of being included in the sample. So here in this example, you can see we have a population of people, and you can see in the sample that I've highlighted in green, those are the people that were selected for the sample. Every person in this population had an equal chance of being included in the sample. The second sampling technique is stratified random sampling. In this technique, the population is first divided out into groups, also called strata, based on different characteristics of the population. So for example, you might have groups broken out by the city that they live in. Then once these groups are created, you randomly select individuals from each of these groups to make up your sample. This ensures better representation of the population based on the characteristics that you determined. For example, if you have divided up the population by city, this sampling technique will make sure that there are representatives from each city in your sample. The third type of sampling technique is cluster sampling. In this technique, the population is first divided into clusters based on specific characteristics, and then the clusters are randomly chosen to be part of the sample. Now, this is slightly different from stratified random sampling because in cluster sampling, the entire cluster, the entire group is included in the sample, not just some individuals from each group. And the fourth type of sampling technique is systematic sampling. In this sampling technique, every nth person in the population is selected to be in the sample. So we have our example here. Let's say we have 15 people and we want to create a sample of 5 people. The way we find the nth number is that we will take the total population and divide it by the number of people we want in the sample. So in this case, you can see we have 15 divided by 5 and we get 3. Which means we will take every third person from this population to be in the sample, which you can see we've done here. Now that we've covered sampling techniques, let's talk about hypothesis testing. Hypothesis testing is a method used to test ideas or claims about a population. The first step in hypothesis testing is forming a hypothesis. When forming a hypothesis for a hypothesis test, we first start with a claim and what we want to test. So if we go back to that loyalty program example that I mentioned at the beginning of the video, in this case, we want to test if being part of a loyalty program has an effect on a customer's spending. So here we'll generate 2 hypotheses for this test. The first is the null hypothesis, and this will state that a loyalty program has no effect on spending. We'll also define an alternative hypothesis, denoted as HA, which states that the loyalty program does have an effect on spending. After we've formulated our hypothesis, we can move on to the next step, which is choosing a significance level. A significance level is a threshold that determines how much evidence is needed to reject the null hypothesis. A common significance level is 0.05 or 5%. This means that you are willing to accept a 5% chance of wrongly rejecting the null hypothesis. Wrongly rejecting the null hypothesis means that you are saying the null hypothesis is not true when in fact the null hypothesis is true. This is also known as a type 1 error. Later on in this video, I'll go over some statistical tests using Python and we'll revisit the significance level and I'll demonstrate how to use it in practice. Once we choose a significance level, we then run a statistical test like a t-test, a chi-square test, or an ANOVA test. These tests will return a p-value, which is the probability that another sample can be chosen from the population that is similar to the sample that the test was run on. Finally, once we have the p-value from our statistical tests, we interpret that p-value. If we get a p-value that is less than our significance level, then we reject the null hypothesis. If the p-value is greater than the significance level, then we fail to reject the null hypothesis. Now let's go over some common statistical tests, and once we know the definitions of them, we'll go over some examples of how to run these tests in Python. So there's a lot of different kinds of statistical tests, but for today's video, I really wanted to focus on t-tests, chi-square tests, and ANOVA tests. So the first type of statistical test is a t-test. T-tests are used to compare the means of two different groups and test whether or not there is a statistically significant difference in the means. There are three different types of t-tests. The first is a one-sample t-test. This is where you compare the mean of a sample to the mean of the larger population. So to run this type of test, you would need to know what the mean of the larger population is. The second is an independent samples t-test, or a two-sample t-test. This is where you compare the means of two independent groups. And the third type of t-test is a paired t-test. In this type of t-test, you compare the means of two related groups, or the mean of the same group just taken at different time points. The next statistical test is a chi-squared test. This test is used to determine if there is a significant association between two categorical variables. This test works by comparing the expected frequencies of combinations of the categorical variables, assuming no association, to the observed frequencies in the data. The larger the difference between the expected frequencies and the observed frequencies, the more evidence there is that there may be a relationship between the two variables. And the third type of statistical test I wanted to cover is an ANOVA test. ANOVA stands for analysis of variance, and it's used to determine whether the differences in means across multiple different groups is statistically significant. So if you have more than two groups and you want to compare their means, you can use the ANOVA test to see if the differences in these means are greater than what would be expected due to just random chance. Now let's jump over to Jupyter Notebook to see how to run these tests using Python libraries. So for these examples, I'm going to use this data set from Kaggle. It contains information about customer spending at different restaurants. So before we get to the test, let me just go over these tables from the data set. So I'm using pandas to read in the CSVs from the dataset. The members data frame contains information about the customers that are going to the restaurants, like their name, their email, things like that. The orders and the order details tables contain information about the items that the customer ordered, the type of meals they ordered, which restaurant it was ordered at, and how much each order cost. Now the meals and meal types tables contain information about the meal that was ordered, so like the type of meal it is and the price. And finally, the restaurants and the restaurant types tables contain information about the restaurant that the meal was ordered at and what kind of restaurant it is. Now that we know a little bit more about the data set, let's move on to seeing how you can run a t-test using Python. So first, let's set up a scenario. Let's say you are a data analyst for a restaurant chain. The restaurant chain has tested out starting a loyalty program by allowing a random sample of customers to enroll in the program. Your boss wants to know if members spend differently after participating in a loyalty program than before they were in a loyalty program. For this problem, you have the spending and order data for 30 loyalty members both before and after the loyalty program started. So if you remember back to the three types of t-tests that we had, which one do you think we would use for this problem? If you guessed paired t-tests, then you are correct, because for this problem, we want to compare the average spending of the 30 loyalty members before they were part of the loyalty program and the average spending of those same 30 loyalty members after they were part of the loyalty program. So since we're comparing the means of the same group at different time points, we would use a paired t-test. So for this t-test, let's set up our hypothesis first. So here our null hypothesis is that there is no difference in average spending before and after participating in a loyalty program. And our alternative hypothesis is there is a difference in average spending before and after participating in a loyalty program. And when we run this t-test, we want to do it with a significance level of 0.05. Now this data set doesn't actually have members tagged as loyalty members, so I just randomly sampled 30 members from the data set and marked them as being part of the loyalty program. So here's the code that I used to do that. Now since we're only comparing the averages before and after being part of the loyalty program, we want to filter down that members data frame to only include members that are part of the loyalty program. And then after we do that, we want to merge the members table with the orders table. This is because the members data frame only has information about the members, and the orders table will have the actual orders and how much was spent on each order that each member ordered. Now, once we join orders and members, we'll get a table that has a lot of columns, so we'll filter it down to just the member ID, the date, and the total order. And when we run this cell, we'll see that our resulting data frame just has the member ID, the date, and the total amount ordered for that specific order. And you'll see that each order for a member is listed as its individual row. Next, let's create two separate data frames for the orders members placed before the loyalty program was implemented and after it was implemented. So we'll use April 1st, 2020 as the implementation date for the loyalty program. So the pre-loyalty data frame will have all the spending before that date, and the post data frame will have all the data afterwards. So let's just create that here. Let's call it loyalty members pre, and that will be equal to orders and members where the order date is less than 2020-04-01. And similarly, we'll create the post data frame to just be the orders placed after the 1st of 2020. And I can just print out one of these just so you can see what that data frame looks like. So right now in these data frames, you can see that we still have each individual order that a member placed, but what we want is we want the sum of all the orders that they placed. So to do that, we'll actually group both of these data frames by member ID and then take the sum of this total order column. So next, we'll group these data frames by member ID and take the sum of total order, which is the amount spent on each order. We'll do loyalty members pre dot group by member ID and we will do a sum of total order. And then we'll also do a sort values so that the member IDs will be in numerical order. And we will do the same thing for the post, but we'll just rename it. And let's print out this new group data frame. And you'll see that each member ID only appears once and it has the sum of the orders. So member ID 4 spent about 9.5 thousand on orders. Now, the t-test function in Python actually can't take data frames, so what we need to do is we need to convert these data frames into lists. And these lists will contain this total order value for each member ID. So let's do that real quick here. So for the pre-period, we'll just call it pre-spending, and that'll be equal to list. And within this list function, we will pass it loyalty members group, and we'll take the total order subset. And here you will see that now what we had before is in a list. So this is that member ID 4's spending, which was about 9.5 thousand. And we'll do the exact same thing for post. Now for the part you've been waiting for, actually running the t-test. So to do so, we need to import the scipy.stats library. And this library has a function called t-test rel. Here we will pass in pre-spending and post-spending. And when we run this, it will return to us a t-test result, which gives a statistic and a p-value. So this p-value is what we will use to determine whether or not to reject the null hypothesis. Now, if you remember, our significance value for this test was 0.05, and our p-value is 0.1098, which means it is greater than 0.05. This means that we failed to reject the null hypothesis. And if we go back and look at what our null hypothesis is that there is no difference in average spending before and after participating in a loyalty program. We failed to reject this hypothesis, so we can conclude that there is no difference in average spending before and after participating in the loyalty program. And that is how you would run a t-test in Python. Now let's move on to a chi-squared test. Remember, this is the test that checks to see if there is a relationship between two categorical variables. So for this example, let's say our scenario is that the restaurant chain wants to know if the type of meal ordered, which has the values of cheese, beef, chicken, or vegan, is related to the type of restaurant, which has the values of Asian, fast food, homemade, Indian, and Italian. So for this test, our null hypothesis will be that the type of meal is independent of the type of restaurant, or in other words, there is no relationship between the two variables. Our alternative hypothesis is that the type of meal is not independent of the type of restaurant, and that there is a relationship between the two. And like the last example, for this one, we'll use a significance value of 0.05 as well. All right, so for this example, we need one table that contains the order, the meal type that was ordered, and the restaurant type that it was ordered at. Now, getting this in one table involves joining 5 different tables, which I've actually done here. Now, I won't get into the details of how I did the joins, but you can see the code for it here. And what you really need to know is this final table has all the details we need in one table. So it has the order, the type of meal that was ordered, the cheese, beef, chicken, or vegan, and then it also has the type of restaurant that meal was ordered at. So for the chi-squared test, we need to import the SciPy stats library again, but this time we will import the chi-squared contingency function. So the first thing we need to do is we need to create a contingency table that shows the observed frequencies of the different categories. So for example, we need to see how many times we see a cheese meal ordered at an Asian restaurant. So to do that, we can actually use Panda's crosstab function. So that's what I'll do here. And we will specify the columns that we want. So we want the frequencies of meal types, meal type by restaurant type. And if we print that out here, we can actually see the number of frequencies we see. So about 2.7 thousand times we see a beef meal ordered at a Asian restaurant. About 4,000 times we see a beef meal ordered at a fast food restaurant. So now that we have that contingency table, we can actually pass that contingency table to the chi-squared contingency function. And this function is going to return 4 different values. The first is the chi-squared stat, then it's going to return the p-value, it's going to return the degrees of freedom, and it's also going to return another contingency table that shows the expected values for each of these cells. So here, we'll just supply a CT table, and we'll actually print out all of those variables to see what it returns as well. All right, so here are our results, and we can interpret these results. So first, let's look at the chi-squared statistic. We have a value over 3,000 here. So this is a measure of how much the observed counts deviate from the expected counts under the null hypothesis, under the assumption that the two variables are not related. A larger chi-squared generally means that the two variables are not independent and that they might be related. Next, we can see the p-value here. We have a p-value of 0, and remember our significance level is 0.05. So we're getting a p-value less than our significance level. We also see the degrees of freedom, which is 12 here, and that's really just calculated by taking the number of rows minus 1 multiplied by the number of columns minus 1. So here we have 4 rows, so subtract 1, so that's 3, and we have 5 columns, subtract 1, that's 4, so we do 3 times 4 and we get 12 degrees of freedom. And here you can see what the expected frequency should be for each category. So here for a beef meal ordered at an Asian restaurant, we would expect that to be around 2,500 instead of the 2,700 that we saw. So to know whether or not we can reject the null hypothesis, once again here we will look at the p-value and compare it to our significance level. So we have a p-value of 0, which is less than our significance level of 0.05, which means that we can reject the null hypothesis. And instead, we can conclude that the type of meal is not independent of the type of restaurant, which means that there is a relationship between the two. And that is how you would run and interpret a chi-square test using Python. Finally, let's go over an example of using the ANOVA test in Python. So for here, let's say we have this scenario where we want to answer the question, is there a difference in average revenue across restaurant types? So here, our null hypothesis is that the mean revenue is the same across all restaurant types, and the alternative hypothesis is that at least one restaurant has a different mean revenue. And our significance level to test this will be 0.05. Now here we want to use ANOVA because if you remember from the previous example, we have 5 different restaurant types. So when we want to compare the means of more than 2 different groups to see if the difference in the means is statistically significant, we use an ANOVA test. So to run an ANOVA test in Python, we'll need to import the SciPy stats library again, and specifically we will import the f_one-way function. So here we want to get the average revenue for each restaurant of the different restaurant types, and we want them as a list. So let's say there's 5 different Asian restaurants. We want to create a list that has 5 values in it, where each value is the total revenue for each restaurant that is categorized as an Asian restaurant. So to do that, we will take this data frame that we created before, because remember this data frame has all the orders with the restaurant types in them. So we'll take that data frame and we'll filter it down to where restaurant type is equal to Asian. And now we want to group by the restaurant name. And we want to take the sum of total order. This will give us the revenue for each restaurant that is categorized as an Asian restaurant type. And we'll just make sure to only pull the total order column. And this ANOVA function, similar to the t-test function, doesn't take data frames, but it takes lists. So we want to store this as a list. And if we print out Asian orders, we'll see we get a list here, and each value in this list, like I mentioned before, is the total revenue for each restaurant type that is classified as an Asian restaurant. So in the data frame, there is 1, 2, 3, 4, 5, 6, 7 Asian restaurants, and these are the total revenues for each of them. So now we want to create a similar list for each of the 5 different restaurant types. All right, so now that we have all of these lists created, we can just pass all of these to the ANOVA function. And when we run this, we will get a statistic and a p-value, which will tell us whether or not we accept or reject the null hypothesis. So here we can see we have a p-value of 0.03. Now remember, our significance level once again was 0.05, and 0.03 is less than 0.05, so therefore we reject the null hypothesis, and we can conclude that at least one restaurant has a different mean revenue. So now that we've determined that the means of some of these restaurants are the mean revenue of some of these restaurants are statistically significant, the next step would be running some tests to determine which groups are statistically different from each other. And there's different tests you can do for that, but that is a little bit beyond the scope of this video. But this is how you would use Python to run an ANOVA test. All right, that is it for our overview of inferential statistics. Just as a review, we went over what the definition of inferential statistics is, went over some sampling techniques, over how hypothesis testing is done, and finally we went over examples of using a t-test, a chi-square test, and an ANOVA test using Python. In the next video, I plan to talk more about probability and distributions, so I hope to see you in that one. Until then, thanks so much for watching this one.